Okay, now I'm recording. Yes, please. Can you repeat?
The hypothesis class here also mean model class.
Yeah, model class and hypothesis class is the same.
Yeah.
Model class or hypothesis class, yes. So the question now is how to obtain these parameters, okay? And so we need to define a notion of goodness, okay, to select these parameters and to select the function in our hypothesis class. So the third ingredient, it's a notion of goodness, okay? And this is formalized thanks to a cost function, or just cost, or energy function, okay? So cost function, we denoted it generally C, capital C, which takes as input a true label that belongs to the training data, okay? And our prediction, okay, according to the current model theta, and it spits a number which is non-negative, okay? Okay, and this number is denoted like this. Okay, sorry. Yeah. But really, you should think of this cost really as a function of the parameters themselves. So of course, this is a function in which you plug a true label, a prediction, and it spits a number. But because we will use this cost as a way to find proper parameters theta by minimizing this cost, conceptually, you should really think of this cost as a function of the parameters themselves, okay? Through the dependence on the prediction function, okay? All right, and concretely, this cost, we write it in as a sum, okay? It decomposes as a sum over the data. Oops. Okay, and for example, when we take the mean square error loss, the quadratic cost, or sometimes I say loss, this is another way to call this function. Okay, you want to minimize the loss. This is more the language of statistics when you use loss. When in machine learning, people say cost, but it's the same thing. In the case of quadratic loss, this is simply the sum of squares, okay? Or the average of the squares, if you want. Okay. And once we have defined this notion of goodness, okay, we are ready to set up the learning problem. And learning becomes what? Becomes finding the parameters, okay, and these parameters will depend on the data, okay, which will be the minimizer of the cost, okay. Where this cost, I denote it like this. I don't write the sum, I write it in matrix form like this, but this is what I mean. Okay. Okay, so you see, conceptually, we are really thinking of this cost as a function of theta itself, because we are minimizing this cost with respect to theta. So here the data, you can think of it's fixed, so it's given to you. So really what we can vary are the parameters, okay? So that's why conceptually it's good to keep in mind that this cost is really seen as a function of the parameters themselves for a fixed data set. Okay, so this is essentially what we reached yesterday. Okay. So now I would like to give few steps that I will call the machine learning workflow. That you need to follow whatever setup you are considering in machine learning, whatever application you are you want to approach, whatever algorithm you are using for the task. What I'm going to say now is true, completely generically, okay? And we will try to understand why. Okay. Is there any question on what we did yesterday, or is that clear? Okay. Okay, so the machine learning workflow is a procedure that allows to essentially answer how to find a good predictive model. And don't worry, if it's still a bit abstract, in 10 minutes we're gonna start an application. We're gonna code a real learning algorithm and to see how things work. Okay. But before doing so, let me give you a generic recipe. So something you have to do before attacking any learning problem, that's why I put a 0. This is the first thing you have to do. So always to keep in mind is to divide the data set into two subsets. Okay. So the whole data that you have access to, okay, you have n data points, which means n pairs of input of size p and associated output. You're going to divide it into two subsets. Okay. The first, I will call it the training set. And the second one will be called the test set. Okay. So is this symbol clear for everyone? So this symbol means the union. Okay. It means the training set and the data set. Okay. This reads n. Okay. And we will require, and this is absolutely crucial, their intersection is empty. Okay. So this operation, so this is mathematically, this is the union. Okay. Sorry for those for which these kinds of things are trivial, but and this is the intersection. And this is the empty set. So this is just a fancy way, this is the mathematical way of writing that there are no sample, and by sample I mean a pair of input-output, okay, that belong to the original training data. there is not a single pair that both belong to the training data and the test data. They have nothing in common. Okay. Of course, all the data that you have access to here, we always assume in machine learning, okay, that's the basic assumption, that all these pairs of inputs and outputs they are drawn independently and identically. Okay, this is what means IID, independently and identically distributed according to some joint probability distribution that we'll call PXY. This probability distribution is unknown. This probability distribution is what fully captures the rule that connects inputs and outputs. This is the unknown thing, the unknown system, the unknown process that you are trying to capture in some way, that you are trying to learn. Okay, this is unknown. And the assumption is that all the data points that you sampled, that you have access to, are drawn IID according to some joint law, joint between input and outputs, which is unknown. Okay, so unknown. Unknown. Okay. So when I say that the training data and test data have nothing in common, what I really mean is that there is no single pair of input and outputs that both belong to the training data and test data. But they are, of course, similar. There should be similar enough, this training data and test data. Otherwise, it makes no sense to train on some data sets in order to predict on a totally different data set. And by assumption, what they have in common, this training data and test data, is the fact that all the pairs of input outputs, both belonging to training data and test data, were generated according to the same underlying probability distribution. Okay? So this is really the basic assumption in machine learning. It is always underlying whatever you're doing. You have data which are randomly sampled according to some unknown distribution, and you are trying to find a good predictive model able to capture this unknown distribution. Okay. All right, so we have divided our data into training data and test data, such that their union gives you back the whole data, and their intersection is empty. Okay, they have nothing. They have no common samples, okay? And typically, okay, you take, for example, 90% of your data goes into the training data, okay? Okay, with n train, the number of training points, which is around 0.9 times n, where n is the total number of data points, while the remaining 10% go in the test data. Okay. Okay. And of course, by construction, you have that n, the number of training points plus the number of test points is equal to the total number of points of samples. Okay. Of course, this decomposition into 90% for the training data and 10% for the test data is arbitrary. This is your choice. If you want to do 50-50 because you have something in mind special, you can. There is no theorem here. There is no rule. This is your choice. Okay. And what is important is that this splitting into training and test data, okay, the splitting is done randomly. Okay, so this would be an absolute mistake to try to select by hand or according to some external procedure which point you think are good points in order to train your models and which one you should use for testing. You should never do that. You have to select them totally randomly. Otherwise, you are introducing bias. Okay, it means that you are already assuming something about the underlying system that is not captured automatically by your model. You are introducing possible source of statistical bias. Okay. Okay. Now we have our splitting into training and test data. The next thing you have to do is to learn on the training data only. Okay, otherwise this division would make no sense. What does it mean? It means that what I was writing before, the learning procedure, which is concretely an optimization problem, a high-dimensional optimization problem, is actually done on the training data only. Okay. I will use, yeah, okay, now let me take a generic cost, but you can always keep in mind the square, of course. Okay. So here concretely, this sum means that you are summing only over the pairs of inputs and outputs that belong to the training set. Okay. All right, and once you've done that, you obtain, again, the predictor, which is our f of theta hat, okay, which is a function indirectly of the training data that was used. What does it mean? It means that, okay, implicitly, this function is a function of the training data according to this training procedure, which means that if you were to change the training data, your model, your learned model, your predictor, your final function, the one that you chose in your hypothesis class, would be different. Okay? So here you have a notion of stochasticity of randomness, the random choice of the training data that has to be random, okay? And we will understand why. We said why, otherwise there is bias. So due to this randomness, the predictor is itself a random function, okay? And once you have this predictor, let's say I give you a new data point that was not in the training set, okay, that was not used to train the model, then you can predict what should be the associated label, the associated output according to your model by just feeding. So you want a prediction of the associated output. How to do that? You just feed your model that you trained on this data point, okay? And it gives you a prediction. Okay? And hopefully this prediction is close to the true one. This is the point. And why should it be close to the true one if this new data point was not part of the training data? Because what you hope is that your training data was a good representative, a good sample of the true underlying probability distribution. And therefore, it captured enough characteristics, enough features to be a good predictor. Okay. Okay. Now, and maybe this is one of the most important point, and this is really the crucial point of machine learning, which makes it very different from classical statistics. Okay. You need to evaluate your model. Okay. Because now that we trained a model, that we obtain a predictor, okay, a prediction function, how can we tell whether we did a good job? Okay. So is someone able to tell me what should I do to evaluate my model? I'll give it a try.
Use test data.
Yeah, exactly. Using the test data. So the purpose of the test data is exactly that, is to evaluate our model. So here, when I say evaluate your model, it is important to emphasize on the test data. Okay. That's the name. It's the data you use to test your model. Okay. Because again, what was the main difference between machine learning and statistics? Machine learning is concerned only, or mostly, at least in those courses, only with prediction. Okay. So are we able to predict the labels associated to new, fresh, unseen input data? Okay. So we have to be able to answer in some way this question. And so we have to use fresh, unseen data. And hopefully we have some fresh, unseen data, because at the beginning, we have divided our data into two separate sets, one that we used to train, and the other, which was not used to train in any way. So this test data is completely uncorrelated to the learning procedure that you used. So it's uncorrelated to your model. So which means that if we test our model on the test data, we have an unbiased estimate of the performance of our model. Okay. Unbiased in the sense that the test data is totally uncorrelated with the model that we trained. Okay, so the performance on this test data should be a good representative of the performance of our model on completely new data that we don't even have access to at the moment, that we'll maybe observe in the future, which hopefully it has to be generated according to this model that was used to generate the training data. Otherwise, we cannot predict, of course. Okay. So we do so, but now we need a notion of error. Okay, we need a metric. We need a notion of goodness again to evaluate our model on the test data. So what is the natural choice? We already defined the notion of goodness, and for that we define the cost function, the energy function. Okay, so what we do is that we compute what I will call the out of sample error out of sample emphasizes that these are an error related to data that was not used for training. So it's out of the sample you used for training. And so this out of sample error is nothing else than the cost evaluated between the predictions of your model and the true labels in the test data. Okay. And you can use the same cost, or you can use another cost if you prefer, but usually we use the same cost. So if you use a quadratic loss, a quadratic cost for the training procedure, you would typically use a quadratic cost here as well. Okay. And here I put what? I put my predictions from my trained model. Okay. This again, I wrote it also like this. And here you see now the theta hat here is fixed. It has been obtained from the training procedure on the training data. And we chose it, now it's fixed. And we are evaluating its performance by computing this error metric, which is the out of sample error. Okay. This one is fixed by training. Okay. And this out of sample error is also what we call, okay, so in books you may see a slightly different definition. You can, but at the end it's the same thing. We also call it the generalization error. The generalization or prediction error. Or at least this is a good estimate of the true generalization or the true prediction error. Okay. Generalization error in the sense that it gives us a sense of how good is the model to predict new unseen data. So how performant is the model at generalizing, which means going beyond the training data. Okay. Again, this theta hat here is fixed and is a function of the training data. Okay. And this quantity, this generalization error, has to be put in contrast with another error, which is what? Which is what I will call the in-sample error. Or simply the training error, which is what? Which is the same thing, the cost, but evaluated on the training data. Okay. So for example, so what do we do when we learn? Okay, here, this is the learning procedure. When we are learning, we are trying to minimize the training error. So learning is equivalent to minimize with respect to theta, the training error. If I see this training error as a function of theta. Okay, that would be that function. This would be the training error seen as a function of theta. So learning is about minimizing the training error. And once you reached a minimizer, you obtain a scalar number, you obtain a number, and you can call that the final training error, okay? Which estimates how good your model is able to fit the training data, okay? So this quantity tells you how good your model can fit your training data. Okay. But here I said that in order to see if our model is good or not, we use the out of sample error, the generalization error. And this emphasizes the main question again in machine learning, which is not, you're not trying to find a model able to fit your data. You are trying to find a model able to generalize on unseen data. So the quantity that really matters is the out of sample error. Okay, this is really what you are interested in. You want to reach a low generalization error. Okay, and as we will see, it does not necessarily mean that you reached a low training error, and this is the whole difficulty of machine learning. And the opposite can happen. It's not because you are finding a model able to perfectly fit your training data, which means finding a model if you find a theta hat after training such that the training error evaluated for the associated model is 0, does not imply that the generalization error is 0. Quite the opposite. As we will see, it's not necessarily a good sign that the training error is too low. And we will try to understand why. In general, what you have is an inequality, is that the generalization error will always be larger than the training error. And all the question is how larger? What you hope is to find a model where the difference between the generalization error and the training error is small, which means that you do not overfit. And we will actually discuss this point in detail. Okay? Because the thing here is that if you have a very rich model, you will always be able to fit very well the training data. I don't remember which scientist, it was a mathematician that said with 6 parameters, I can fit an elephant. Okay, you take a function parameterized by 6 parameters, and if you put the coefficients properly in front of this complex valued function, and you draw this function in the complex plane, you can draw an elephant with just 6 free parameters by just tuning them. Okay. And here it's the same. If you have enough free parameters, you can fit whatever data that you want. It can be extremely rich. You will always be able to find a model fitting this data if you allow for enough richness. But this does not mean that it will be good at predicting. And that's the whole point. Because if your data is noisy, is finite, you may fit actually random patterns, which comes from noise. And therefore, this would lead to a very bad prediction performance. Okay, and this is what we want to understand now. Are there questions before I move to the coding? Yes.
But we have the test data and the sample data from the same source. So why there is a difference?
Say it again. I'm sorry.
I mean, we take the test data and the sample data from the same source. we just divide them. So why there's some models it gives the good result. I mean the low cost in the training, but when we test it with the test data, it gives bad result.
No, because you said something wrong. You said that these two errors are obtained from the same source.
No, I mean the two data, the test data and the sample data, we take it from the same source because we just divide it.
Yeah. So
we have data and then we divide it.
Yes. By hypothesis, the training and test data are always coming from the same source. And what you mean by source here is this joint law, this joint distribution. So yes, the test data and training data are made of samples that are drawn from the same joint distribution, from the same source. This is true. But it does not mean that once you fit the training data, you found a model that is perfectly able to capture this distribution. Okay, maybe you find a model which is good enough to describe the training data, but think in the extreme regime where you have almost no training data. You will find many ways of fitting this training data, yet most of them will not be correct to predict. Okay.
What if I have a very large training?
That's
training
a very good
data.
question, and we will explore right now all these questions while coding. Okay, but to answer your question, if you have infinitely many data points, okay, actually the empirical distribution of the data is then equal to the true statistical distribution. Okay, so if you have very, very many points, you are able to completely reconstruct this distribution. And therefore, in this case, the training error and the test error should be the same, because both the training data and the test data would contain enough data to fully capture the distribution. And so you would not have a difference between the two. But the point is that in machine learning, you always have access to a finite amount of data. And this creates, so the data can be noisy intrinsically, and it is finite. And this finiteness of the data is a source of noise also. Okay. So let's see that. And here, let me just say a last thing. Imagine that you have two algorithms or two machine learning procedures that you want to use for some tasks, to solve some tasks. Let's say you have a neural network on one side, which is a fancy algorithm. And on the other side, you have a linear regression, which is just trying to find a linear fit for your data, a linear relationships between inputs and outputs, so the simplest possible rule. And you want to know which one is the best. What you do is that you train these two procedures on the same training data, and then you test both results, both predictors on the same test data, and you will see which one gives the best. Okay. Or if you have different versions of the same algorithm, let's say you have multiple neural networks architectures, or you have multiple linear models, but with a different number of features, etc. You can choose which one is the best by training both of them on the training data and testing them both on the same test data and choosing the one which has the smallest test error. And so choosing a model, okay, by minimizing the test error is called cross-validation. Okay, and this is the unique single recipe to choose a model among different classes of model. Okay. All right, so let me now open the notebook. Let's discuss a bit what is going on. Where is it? No, wait, I should stop sharing this. Stop share. Okay, and I will do stop share. Okay. All right. So I hope you had a look to that. I will scan through it, but yeah. All right. So what we want to understand with this notebook is something simple but very deep question: is why is machine learning a difficult problem? Okay, why is it difficult to learn from data? And by learning, we really mean.
Can you please zoom a little bit?
Yes. Still like this, it's okay?
Yes, thank you.
Okay, so yeah. All right, so we will solve a very simple task, which is called polynomial regression. So it's a regression problem. Okay, we want to predict things about continuous, about real valued variables. And it's called polynomial regressions because, as we will see, the features of the data will come in the form of polynomials. And the model that we'll use also will be a polynomial. Okay. All right, so okay, let me read. We want to fit data with polynomials of different orders. This goes the name of polynomial regression. So we will see essentially how things change when the data is noisy and finite. So essentially, I want to answer exactly the question of this person that asked them 2 minutes ago. And even if the task is simple here, it contains all the difficulty of more advanced machine learning problems. Okay, so take this notebook seriously, and I strongly advise you to play with it after the course a bit more to gain intuition, because this intuition will extrapolate to much more complex problems. So consider a data set, okay, outputs and inputs. We have n data points, okay, and in this case, the x's, okay, the inputs will also be real numbers like the outputs, okay, so it's a simple data set. And we will see that these x's will take them as IID random variables between 0 and 1, okay, uniform variables in 0. And the unknown rule that connects inputs and outputs, the ground truth rule, if you want, which is unknown to us as statisticians, is of the following form. Yi, the output, is some function f applied to the input x plus Gaussian noise, okay? And of course, the function f is unknown, and in general, you don't even know that the noise that has been added is additive and it is Gaussian. You don't know all that, okay? The only thing you know is the data, okay? But in this ideal model, we will generate these outputs like this, and the noise will be centered, and we'll have a identity covariance, so it is uncorrelated, okay, with variance equal to sigma square. So we'll call this unknown function the true features, in the sense that it's the true rule that generates the outputs, okay. As always in machine learning, all data points in the training and test sets are assumed to have been generated independently from the same unknown joint distribution. This is what I said before. This joint distribution would be known if the function f and the model of the outputs, which are conditionally on f of x, they are Gaussian random variables because we have additive Gaussian noise. If we know this form, we would know this joint distribution. There would be no task to solve, okay? But of course, all that is unknown. The only thing that we know is the data set. Okay. So now we need to define a model class, an hypothesis class, okay, in order to make predictions. So what we will assume is one of the simplest possible class, which is the class of polynomials up to order alpha, okay? And this class, this hypothesis class, will be parameterized by a vector theta index alpha, which is of size alpha plus 1, which are the coefficients in the decomposition of this point in the polynomial of order alpha. So the first coefficient is a constant. The second coefficient is the coefficient which is in front of x. The third coefficient will be in front of x squared, and so on and so forth. So here is our polynomial. Okay. These functions represent the model or hypothesis class, and we will use such functions to make predictions. Okay. And this function encodes the class of features that we are going to use to represent the data, which in this case are polynomials. So here it must be clear in your mind that sometimes the data that is given to you is what it is, and it has different features, and you don't have to change anything before processing it. But sometimes you have to process it to define features from the data, okay? Or maybe sometimes you have certain features that you want to keep in your data and some others that you want to process in order to redefine new features. This depends on the application. In this case, the data is extremely simple. The inputs are just scalar numbers, are real numbers. And we as statisticians are defining new features, which in this case are all the monomials of this variable. So by monomials, I mean just different powers of this number. So the zero order monomial is x to the power 0, it's just a constant. And the associated coefficient is theta 0, is what we want to learn. The second feature is just the point itself, x, and the associated coefficient we want to learn is alpha 1. The third feature that we are creating is x to the squared, and it has an associated parameter that we need to learn, etc., etc. Okay. So our task is to learn the parameters, namely the weights of each features. Okay. And so to do so, we will train our model on training data. Okay. And test afterwards the effectiveness on the model on a different data set, which is the test data, which are different data sets such that their union is the whole data. Okay. And that have nothing in common. Okay, this is very important. Otherwise, you create bias. The point of dividing the data into training and test data is that in machine learning is concerned with making accurate predictions about new data we have not seen. And as we will see, models that give the best fit on the training data do not necessarily make the best predictions on the test data. Okay. And so if we didn't have test data, we could not realize that. Okay. And this is the whole difficulty of machine learning. All right. So we'll consider two situations. So in the first case, the process that generates the underlying data, which means this process here, this rule, will belong to the model class that we use to make predictions. What does it mean in polynomial regression? It means in a case where the function, the true function underlying the relation between input and output, is itself a polynomial of an order which is low enough to be included in our hypothesis class. Okay. In the second case, which is a more realistic case and what mostly happens in real applications of machine learning, the true features, the true model underlying your data is not contained in your hypothesis class. Even if your hypothesis class is rich, in general, it's even hard to define mathematically what is the rule that generates images of dogs, right? So, so in this second case, the true features in this function f will not be a polynomial, or this is what we'll consider, will be a polynomial, but of order higher than what we consider in our hypothesis class, which means our hypothesis class will not be rich enough to really capture the true relations between inputs and outputs. Okay, so this first case where your hypothesis class contains the ground truth model is called in machine learning the realizable setting. Realizable in the sense that the model is contained in your hypothesis class. You can realize with your hypothesis the true model. In this case, the more realistic case is called non-realizable setting. Okay. But even if it's non-realizable, it does not mean that you are not able to predict well enough. Okay. So we'll consider three model classes. The first model class will be the set of polynomials up to order 1, which means just linear models, a constant plus a coefficient times x. Okay, it's just a line. The second class will be polynomials up to order 3, and the last one will be polynomials up to order 10. So of course, the third class contains the second class, which itself also contains the first class, right? We have classes that are richer and richer. So do you think that, before entering more details, do you think that it's always, would you always select this hypothesis class in our machine learning problem here? Do you think it's, if you have the computational power to train a richer model, to train on a bigger hypothesis class, do you think it's always better? And if yes, why? If no, why?
It is like the Taylor expansion, so we can expand everything based on the polynomials, but I think it consumes a lot of computational power.
But let's forget computational power. So are you saying that it's always better to consider this class?
Maybe
No.
it be dependent on the question itself. For some problems, maybe it'd be easier to use another function.
Okay, so that's a partial answer. The answer is it depends. Okay, and I agree with you. It depends. So do you have another try?
Yeah, for instance, a polynomial of order 10 won't work for a linear model.
That's not true. A linear model is a polynomial of order 10 where most coefficients
all coefficients are equal to 0. So
yeah, but so you can fit a linear model with a polynomial of order 10.
Maybe it depends on the range of the data.
On the range of the data, okay.
I think if we have polynomials of order 10, it has a higher chance to have overfitting.
Yeah, that's precisely the good answer.
I think it's better to do a learning curve before you decide which thing you should do.
Yeah, so that's the purpose of the test data. It will be to see if we restrict ourselves to one of these classes, which one gives the best prediction error, right? So here we have three hypothesis classes. We will train models. We will train the three models and select one function in all of these classes. And how to select the best? By computing the test error and see which one is the best at predicting. But what I claim is that even if polynomials of order 10 include polynomial of order 3 and 1, so they are richer, it's not always good to consider richer hypothesis classes because you can overfit which means you can fit in the training data purely random patterns that are coming from noise. And here you see, we will train our model, which is noisy. We will have noise controlled by this variance, sigma squared. And you see that if you have a very rich function and the noise is high, most of the fluctuations in the data will be dominated by the noise. And so you will fit just the noise. And therefore, your model will not be good at predicting. While if you have a model which is less rich, it is more robust because you have less parameter to fit the noise. And therefore, it is less sensitive to the fluctuations of the noise. Okay, so let's see that. So, all right, to measure our ability to predict, we define mean square error. Okay, so the cost is quadratic here, what I call also the square loss, which is of this form. So now you should recognize this form. Okay, and this is the test error. So I sum over the test data points. Okay, these are the inputs, these are the labels, and this is our predictor, our prediction function. We want to minimize this quantity. And how do we obtain these parameters? The learned parameters are obtained by minimizing, okay, by taking the argmin of the training error. Okay, the training error is a sum of the square differences between our predictions and the true labels on the training data only. And concretely, okay, when we consider a linear model, and here our model is linear, okay, in the sense that it's linear in the thetas, okay, because it's just a sum of thetas times monomials. So it's a linear function of theta. You can just represent this as the inner product, as the scalar product between the vector of weights of parameters theta and the different powers of your data. It's clear? So this x here, so the training error in this case can just be written as the square difference, the L2 norm, between the matrix X, the design matrix or the input matrix, times the vector of coefficients minus the vector of labels. Okay, this is just a more compact way to rewrite this thing, because our model here is of this form. It's just linear combinations of the different features. And the features here are just monomials of our data X. Okay. For example, if you, so this data matrix is of size n trains times alpha plus 1. Each row is a different sample. And the number of columns, which means the number of features, is alpha plus 1. And each column is what? Is a different power applied to our original data point. Okay, so the first column is just constant. It's the constant feature. The next feature is the point itself. The third feature is x to the square, and so on and so forth. Okay? So the columns of the matrix are the features and represent the observables of the systems that are accessible from the data. Sometimes it's given by the problem, sometimes to be constructed, as in the present case. So I just repeat myself. A bit of redundancy is never bad. Okay. And these features are what we think are useful in order to predict the outputs. Okay. All right, so we want to minimize this training function, and this is what we'll do. And actually, let me just tell you that because this loss here, this training error is quadratic, and inside the function is just linear in theta, solving this problem, which means finding the minimizer of this function, is called least square regression, and this is one of the problems we'll study the most. Okay, in the sense that you are minimizing, you are finding the least square estimator, you are minimizing a square error, okay, for a linear model. okay, linear least square, okay? And because this cost is quadratic and inside is linear, the solution is unique. This is a convex function of theta, okay? It's convex, so it has a unique minimizer, and therefore there is no problem in, there is no ambiguity in the solution. It is unique, which is good. And also we can find it easily, okay? In this case, there is a closed expression, and we will study that in the next courses. Usually there is no closed expression, and even in certain convex problems, there is no closed expression, but at least you know the solution is unique. And how to find the solution of a convex function, you can just start from a random point and follow the gradient until the gradient is 0, and it's called gradient descent, and we will study that. But for this simple least square problem, the solution is direct. We will see that, okay? All right, so we start by considering different cases. So one case will be that the rule between inputs and outputs is just a linear rule, so very simple. And then we will consider a case where the rule, okay, the relation between inputs and outputs up to noise is a 10th order polynomial, okay? And we will see what happens when we try to learn on these different, in these different settings using our different hypothesis classes, okay? Okay, so let's see what happens. So we'll start with the case where f of x is linear. We'll use few data points, and we'll first consider noiseless case, and we will consider the free hypothesis class. So here is the notebook. Essentially what it does, what you have to play with is the number of training points, the standard deviation of the noise. Here is the training data. So it just generates uniform points between 0 and 1 and train of them. And here is the noise, it adds them. So I will not go into too much details. You have to be able to read the lines of basic Python notebooks like this, okay? Here I'm defining the model. So how the true labels will be generated from the inputs. This is the linear model, and this is the 10th order polynomial. S is the noise. And here I obtain the data according to this model, okay? And here is where I do this linear regression. This is the model that this is an object that constructs the linear regressor. Here I'm fitting the data. I'm just asking to solve the least square problem I discussed with inputs given by x and the outputs given by y. Okay. Okay, and then I will plot what is going on. Okay, so I let you decode these lines, and here I'm doing the same but with third order polynomials. And the first line here is just doing what? It's creating a matrix of features where the first column is constant, the second one is just x, the various samples of x to the power 1, the second column is the various samples of x to the power 2 up to the power 3, okay, degree equal to 3. And now I'm doing again the least square, I'm solving the least square problem, but now on this expanded matrix, where now the features are all polynomials up to order 3, and I'm fitting on my training data. The fitting is done. Yeah, it's done here. I'm fitting on my training data the model. Okay. Sorry, the fitting is done here. Here I'm constructing the object. The fitting is done here. I give it the training data x and y. And then I'm plotting stuff. Okay, I will plot the cost, the training error for the free hypothesis class. And then we will test on the test data. But at the moment, we just consider the training error. And here I'm doing the same, but for the 10th order polynomial, where the hypothesis class is the class of 10th order polynomial. And here I'm showing results. Okay. So let's start with a case where I have, let's say, 10 training points. It's not much. And the noise will be 0. Okay. I'm running my code. What do I observe? All right. So the training data are those, sorry, so I want to start with the case where the true model is linear. So I will put linear model. So the rule between y and x is just 2 times x, which is there, plus noise. And I have no noise in this case. What happens? Okay, so what happens is that the blue points are the training data, which are essentially uniform points between 0 and 1. Okay, I have 10 of them. The true model, the linear fit, our linear prediction on this training data, for the free hypothesis class, they completely collapse on the true model. Okay, and why is that so? Was it predictable?
It's from 0 to 1. So they are the same.
Yeah, but the thing is that you see, and the training error you see is 0, essentially 10 to minus 31 numerically, it means 0. The training error is 0 for all free models. Why?
Because there is no noise.
There is no noise, and the true model is linear. And our free classes, our free hypothesis classes, they all include the true model. And so therefore, if there is no noise, so the data is completely clean, and our hypothesis class are rich enough to contain the true model, then we are able to fit completely the true model. Okay, so there is no discrepancy. And now if we generate test data, and I will allow myself now to have test data, which will be a bit, that will go beyond the range on which we trained. The range on which we trained was going from 0 to 1. Now we'll go up to 1.2. I have 200 data points, okay, test data points. I'm generating the test data points according to the same model here, okay. And let's plot what happens if we use now our models to predict on these test points that were never seen during the training, okay. We see that the test error, or the generalization error, the out of sample error, is again 0 for all free models. And we see that all the models, they perfectly collapse on the same line, which is the true rule that connects the inputs and outputs. Okay? All right, so good. We learned that if our hypothesis class contains the true model and there is no noise, the fitting problem and the prediction problem are basically the same. Because once you completely fit the true model and there is no noise, of course, you can predict perfectly. Okay? But of course, in reality, there is always noise. Okay? So let's see what happens if I put a tiny bit of noise. Not much. 0.1 of standard deviation. This is really low. Okay. Let's see. All right. So we see that, you see, because the noise is low, all the points are still nicely on a line like this. So all our models are able to nicely fit them. Okay. But we see some wiggles here that appears for the 10th order polynomial that we used. Okay. Why is that so? Because you see, actually, if we were able to zoom on each of these points, we would realize that only the 10th order polynomial is really passing through all the points in this case. Why is that so? Because you have 10 degrees of freedom in this model, actually 11 for the 10th order polynomial, and we have 10 data points. So you are able to perfectly fit them. Okay. And this is what happens. And indeed, we see that the training error for the 10th order polynomial is 0. And we also see something that may look weird, but that's actually the case. The linear model gives a worse training error than the polynomial of order 3, even if the true model is linear in this case. Okay. Now let's see what happens on the test data. What do you expect? Which one should be the best? given that the training error is 0 for the 10th order polynomial? You have a guess? Okay, so let's see. The naive answer is that the 10th order polynomial will perform the best, because on the training data, it gave perfect error. But actually, it's quite the opposite. Okay. Even with a very low noise, you see that now the test error of our 10th order polynomial is extremely high, while, okay, in this case, the best model is the true one, is a linear one. Okay. But what happens? You see that because your 10th order polynomial is very sensitive in the sense that you see if you change a bit the coefficients of the higher order monomials of x to the power 9 or 10, when x is large, or let's say not too small, it has a big change in the value of the function. So your model is very sensitive to the presence of these higher order monomials, of these higher order powers. So these higher order powers are what allow you to perfectly fit on the training data. But this is also the reason why your model is not robust to small fluctuations due to noise. It's because small differences in higher order in the coefficients associated to the higher order monomials lead to very different predictions. And you see that after the last point that we trained, because the coefficients are not exactly good, we see a large deviation like this, and therefore the error here, the test error, is completely dominated by the error at this level, which is away from the range that we used in the training data. So we understand one thing is that even for very low noises, using a rich model may not be a good idea. Okay. And we see also that it's difficult to predict what happens outside of the range that we used for training. Okay. Now let's see what happens if we increase the number of data points, or if we increase first, let's say the noise point, now it's 1. Again, we are completely able in the test, in the training data, with our 10 order polynomial to fit the 10 data points. We have enough degrees of freedom. And indeed, we see 0 here, while the errors of the 2 other models are much larger. Okay. The training here, the 3rd order polynomial looks the best. Let's see what happens on the test data. Okay. So you see that now the test error of the 10th order polynomial is even bigger than before. And here, again, the linear model is the best. Okay, but it's not so far from the 3rd order polynomial. Okay, so the 3rd order polynomial is in red, and the linear model is in yellow, and the true model is in black. Okay, so you see also by eye, it's not so clear that the 3rd order polynomial is better at prediction. It looks like the, the linear model is better. So this looks obvious actually in this case. Okay, let's now increase. Let's change a bit setting. Let's increase the number of training data points to 100. We still have noise. Again, the 10 order polynomial is better. This will always be true. Okay, if you have a larger hypothesis class, a richer hypothesis class, the training error for this hypothesis class will always be lower because you are able to fit better the training data. Okay, you have more degrees of freedom. Okay, the training error seems the lowest for the 3rd order polynomial. Let's see what happens on the test data. Okay, again, the 10 order polynomial gives us complete noise. And the linear model is the best. Okay. Now let's make things a bit more interesting. Let's have a model, the true model that generates the data is a 10-order polynomial. Actually, it is 2 times x minus 10 times x to the power 5 plus 15x to the power 10. Okay, so this is the true relation connecting inputs and outputs up to the noise. This is the function f here. Okay, which is unknown, which we don't know as statisticians. All right, so let me start with a noiseless setting, and let's say few points again, 10 training points. What do you expect? We have enough data in this noiseless case to perfectly find the true model, which is in black, which is below our fit according to the 10-order polynomial, because our fit found exactly the true one. Okay, it found the proper coefficients, and this is possible because the noise was 0. Okay, and the linear model is doing the worst in this case. This is the best linear fit for this training data. And the best third-order polynomial is this red line. And let's see what happens on the test data. What do you expect? Which one should be the best? It should be the 10-order polynomial. We have no noise, so essentially this 10 minus 8 is due to numerical noise, but this should be 0. The test error of the 10-order polynomial is 0, and we see indeed that even away from the range in which we trained, our prediction is perfect because in the training data there were no noise and we had enough. The linear model is really bad, and the third-order polynomial is better. Okay. All right. Now let's make things more interesting and less intuitive. We put a bit of noise, let's say 1, and we train. Of course, as before, because we have 10 data points, the 10-order polynomial fit them perfectly. This is what we see. But, okay, here is the picture. It looks more and more abstract. At some point, you can generate random, you can put that in a museum. And here on the test data, what happens? Something unexpected. The 10-order polynomial is what gives the worst prediction again, even if the true model is a 10-order polynomial. And actually, in this case, the best at prediction is a third-order polynomial. Okay? Because you see that what we fitted was essentially pure noise, and therefore, on the test data, this noise is uncorrelated with what we fitted. We are not able to predict at all the outputs for the test data, and especially away from this range due to this hypersensitivity of our 10-order polynomial to the noise fluctuations. We fitted coefficients that give us total something completely wrong outside of this range, and therefore the error, this number, the test error, is dominated by the discrepancy between what we should predict, which is there, and what we actually predict. Okay. Wait, is there a miss? 1 second. Sorry, 1 second, because the test data, there was, okay, I have a mistake. Give me 1 second. Yeah, I know what it is. Sorry, because actually on the test data, it was still considering the linear model of before. There was a mismatch. It's because I changed something last minute, which you should never do before a class. I did that on purpose. It's for you to learn when you will teach. Okay, data. That should be good. Okay, yes. But still, the conclusions are the same. Okay, magic. So, okay, we have our, the true model is our 10-order polynomial, which is the black line. But still, our 10-order polynomial used for the training is still the worst by what I said before. Okay, it's super sensitive to the noise of the training data. And therefore, we were not able to correctly capture the true rule, the true relation, which is in black. And in this case, the best prediction is obtained thanks to the third-order polynomial. Why the third order? Because given this data set, having a polynomial of order 3 seems to be the best trade-off between model complexity, model richness, in this case, the number of monomials in our decomposition, and the fact that we have stochasticity due to noise and due to the finiteness of the data. So the best trade-off is in this case the third order polynomial, in the sense that it's rich enough to capture sufficiently many features of this black curve, of this 10-order polynomial. So you see the red line that we fit is not so far from it. But at the same time, it's robust enough to noise due to the fact that it has few degrees of freedom, and therefore it's less sensitive to noise. Okay. And you will see that even if let's take even smaller noise. So let's take more training data to see what happens. 100, and we keep the noise at a standard deviation of 1. So the true model is still a order 10 polynomial. Again, as always, the 10-order polynomial gives us the best training error. But on the test data, let's see, it gives again the worst, even if you have more data. You would really need to have a huge amount of data to start to average out the effect of the noise, if you want. Okay, so you see now our 10-order polynomial is more is closer to the true model, the black line, even a bit away from 1, actually no, and suddenly you have a divergence like this. Okay, let's put even more data points. 1000 for the training. Okay, so we see that on the training data, the true model in black and our blue line seem very close. Let's see if it predicts well. Okay, in this case, you see we have enough data. Given the amount of noise in the data, we have enough of it to average out the effect of the noise. Okay, at least in this range, up to 1.2. But if we go a bit, if we try to generalize a bit more away, we go to 0.5. Again, we see at some point that we have a discrepancy that got too big. Okay, so here it looks close, but actually you see if you are here, what you predict maybe is there, and the true model is there. So actually these two lines, the discrepancy at this level here leads to a very high test error, which leads to this high number. In this case, the best model is the third-order polynomial. Let's put 0.2 again. Okay. Let's go again to 100 data points for the training. And that's the end of the course, essentially. All right. So I strongly suggest you to play a bit with these experiments and to get this feeling. You know, try random parameters here, the number of training points, the noise variance, then the range above which you are trying to generalize here, the number of test points, and try to get the answer a bit in advance to get the feeling of what will be the best or not before looking at the plot to see if your intuition is good. Because you see, we understood many counterintuitive things that I will summarize before leaving you. Okay, I will quit here. Okay, so let me write the key points that we understood from these experiments that may look naive again, because we're just doing polynomial regression on very simple data and so on and so forth. But let me be clear again on that point. The thing we understood on these experiments contain all the difficulty of much more advanced machine learning tasks. Okay, this is this competition between simplicity of the model, which allows more robustness to noise, and the fact that at the same time, if you don't have a model rich enough to capture the complexity of the task at hand, then you won't be able to predict. So there is a trade-off, and this is what we'll understand next time. Concretely, mathematically, we'll formalize this idea, which is called the bias variance trade-off. So this is what we'll do next time. I advise you to look at the chapter 2 or 3 in the notes. You will read about that. But first, play a bit with the numerics. All right, so let me just say a few things we understood from these experiments, which apply generically to machine learning. One, fitting is not predicting. Concretely, what does it mean? It's not because you are properly fitting the training data that you will be able to properly generalize, properly predict on new unseen data. Okay? You need to fit training data in some way in order to learn, but it's not because you fitted it correctly or even perfectly that it will predict correctly. So that's why you need this training and test data to see whether you are good at predicting after you trained. Using a complex model, complex or rich model, like our 10th order polynomial, may lead to overfitting. Overfitting means what? That you are fitting random patterns in the training data that are just due to noise, which have nothing related to the actual rule between inputs and outputs that you are trying to learn. Okay, and you have enough degrees of freedom in your model. If your hypothesis class is rich enough, you will capture these random patterns, which will lead to bad prediction performance. And this is called overfitting, fitting too much the training data. Okay. For complex data sets and small training samples, which means few, if you don't have enough data, simple models are generically, let's say, are often better at prediction. Okay, because they are more robust or similarly less sensitive to noise. Okay, and finally, it is difficult to generalize away from the range used in training, or said differently, in situations not encountered during training. Okay? So this just says that predicting is hard. Okay, the machine learning problem is difficult. Okay. All right, so it's good for today. If there is any question, please do not hesitate.
Can I?
Yes, you can.
If we add a term that assumes that it is noisy, then
Can you repeat? Can you repeat? Sorry.
Wait. If we in the G sub alpha, if we add a term,
yes.
Huh?
No, go on. Yeah.
If we add a term that assumes that it is noisy, then that 10 order polynomial will be good. The performance of the 10 order polynomial will be better.
I didn't catch the middle of the sentence. So if
No,
if your hypothesis class is 10 order polynomial, yes.
But we add a term for the noise. So then the performance will be better.
If you add a term for the noise, you say if you are trying in some sense to include in your model the presence of the noise.
Yeah.
Yeah, you can do that, but if you want to include stochasticity like this, you need to do Bayesian statistics, and I will discuss that. But essentially, so this I said it at some point when you assume that the cost, so in the model we were considering, we have a linear model like this. When you assume a quadratic cost like this, okay, implicitly you are already taking into account that you have Gaussian noise. And we will understand that in detail, not the next time, but the time after. I will explain why is that the case. But actually, it's very simple to capture, because you can think of this quadratic cost, okay, if you are minimizing that, it is essentially the same as maximizing a probability of this form, okay, which is proportional to an exponential with a L2 norm difference between your linear model and the labels. And this density, this probability distribution, is the one of a Gaussian. So that's why when you are minimizing quadratic loss like this, what you are doing is actually maximizing the likelihood of the data according to a Gaussian model. I will explain that in detail. Okay.
Okay, I have a quick question.
Yes.
Maybe Yeah, maybe you answered it. So what is always the relationship between the test data and the data we are trying to generalize? Because you say that we are trying to predict something in the data which we don't know. So my question is that what is the motivation of choosing the data I'm going to test on such that I generalize it on the data that I don't know?
Yes. So the underlying assumption that we always make in machine learning, and which in some sense has to be true, otherwise you cannot predict anything, okay, is the following, is that you assume that the data you have access to, which are pairs of inputs and outputs, okay, they are always generated. They are independent random variables, which are generated independently and identically. So this IID means independently and identically distributed. Okay. You assume that all your samples are IID according to some unknown probability distribution. Okay. So the common point between the data that is in your training data and the one that you put in the test data is that they were all generated according to the same joint distribution, to the same process. And therefore, what you hope is that in the training data, there is information about this unknown process, which will be that you will be able to capture, that will allow you to predict what happens for new points that are also generated from the same process.
Okay, it makes sense. Thank you.
So I see questions on the chat. Why do we put noise? I thought the noise we get from the data. No, so in the model we are studying today, I was putting an explicit noise because we were creating fake experiments, so we had to generate the data, right? So this noise was the noise inherent to the data that we were putting there. Okay, we were generating fake data, and to generate fake noisy data, I had to add noise. Okay, so that's why there was noise. But in real applications, you will not add further noise to your data. Of course, in a real application, the data is given to you, you measure it, and you do learning with it without making it more noisy, of course. Okay, but today we were doing experiments, so we were creating the data ourselves. So I was making it noisy. Can you explain the difference between underfitting and overfitting? Yes, so actually I will spend the whole course on Friday to explain this difference. But essentially overfitting means that given the amount of data that you have access to and the level of noise in this data, you consider an hypothesis class which is too rich, okay, which is too complex, and therefore you will fit random patterns that are due to noise. This is called overfitting, okay? Underfitting is the opposite. It means that you are considering a model, an hypothesis class, which is not rich enough to capture the complexity of the rule that connects inputs and outputs. Okay, so for example, think you can repeat the experiments we did today, where you take a 10-order polynomial for the true model, you put no noise in the true data, and you try to train a linear model on it. What you will see is that you will be very poor at predicting, even if there is no noise, because what you will obtain is a linear model, while the true model is 10 order, and therefore you will not be able to predict correctly, because the model you assume is not rich enough to capture the true model. It's called underfitting. And what we want to discuss next time and to understand is how to find the perfect balance, the perfect trade-off between overfitting and underfitting to be at the right sweet spot. Okay. Can you talk about Gaussian process regression? We will mention related things when I will discuss Bayesian inference, but we will not discuss in detail Gaussian process regression. If you want to send me a mail and ask me a precise question, I'm happy to try to answer, but I will not discuss it right now. All right. Is there another question?
Yes. Right. The course on Friday at what hour? What time? Sorry?
Yes, it's at 4:30.
Okay. Okay. Thank you.
Yes.
Thank you very much.
Yes.
Sorry, I would like to know, will we cover something called recommended systems and image segmentation and so on? No, I'm asking, will we cover this?
If we will do that in the course?
Yeah.
No. We'll be much more so humble. Yeah. No.
So this is a basic thing of machine learning.
Yeah, I mean, this course is really about understanding the fundamentals of machine learning, but I will not do advanced techniques. Okay, so this is an introductory course. If you want to understand things about specific advanced techniques, you should go elsewhere. And recommender systems, for example, is not a supervised learning problem. It's an unsupervised problem. And it's related to clustering. So if you want to look about that, I think you should look at clustering. And in the review on which I'm basing the course, you have many things about this. So you can just read there. Yeah.
So we will cover PCA also or not?
No, we will not cover. I will just do supervised learning. So essentially, I will do linear regression, then logistic regression for classification, then the perceptron, which is the simplest neural network, and then we will do slightly more advanced. We will discuss a bit deep neural networks to try to understand what are these machines, and that's it. Yeah.
Okay, thank you.
Okay, I'm having my last question.
Yeah.
So from what we have done from the three polynomials, like we say that the one that fits the test data very well is the one that we will use to work on the generalized data, right?
Mm-hmm.
Yeah, so can't we have some cases where the one that we think that doesn't fit well, it happens that it is the one that can help us in fitting the generalized data?
So you mean cases where if you select a model which has the best prediction error on the test set, at the end is not the best in a real for new fresh data.
Yeah. From what we are having from the three of them. So or it is always true that
no.
This one that fits.
You know, things are only always true in mathematics. You know, things are always true in certain asymptotic limits when the number of points the number of samples go to infinity. Okay, as long as you are in a real practical setting with finitely many data, anything can happen, but there is no, you know. So there are a whole field actually, if you are interested about that, which are called pack bounds, which tells you that there are people that spend their entire career on computing, on giving bounds on precisely what you are asking, in the sense that if you select some model with a certain performance on some data sets under certain conditions, what is the probability that for new fresh data on which you did not test at all, you have a certain deviation from the training error you measured on the test data, and you can obtain bounds on that. And And there is a whole theory connected to that. It's called statistical learning. Okay.
Okay.
And people do their career on statistical learning, but we will not do statistical learning. It's this is a whole course in itself. But in general, in practice, you should select the one that gives you the best test data, the best test error. Sorry.
Okay.
Sorry, I have another question. So here you only evaluate the model, or you decide the predictive power of the model based on the cost function.
Mm-hmm.
But suppose we have like classification model. So in that model, I can let the model cheat, like I just create a loop, and the loop always gives me output 1. So I think in that case, I can't decide, I can't build my decision based only on the cost function. So I have to get another value, single value, that can tell me if the model is showing good predictive power or not. Am I right? Or?
So you said that you cheat in the sense that you corrupt your data?
No, in the sense that I can create a loop in the model, and the loop gives me an output 1 always. So like by doing that, I can get very small cost function. So in that case, the error will be very small.
Yeah, but when you do that, you are
a good evaluation of the model.
No, of course, but I mean, if you, I don't understand the point of generating data which is always 1. Then it means you are learning. There is no structure to learn. If you generate data which is always constant, then
no, what I mean, I have the data already, but what I am cheating is the prediction of the model.
Okay, you change the prediction. Okay.
Of the model. So and of course the cost function will be based on the prediction of the model.
Yes.
So because it is just the difference between the actual value and the predicted value.
But it will be high.
Yeah.
This error will be high. Yeah,
it will be high, or it will be small. If it depends on what I am going to predict exactly. Like what I'm going to classify. Is it am I considered the positive, or the correct answer is 1, or the correct answer is 0? But what I am asking is the cost function only enough to evaluate the model, or to decide whether the model is showing high predictive power or not?
I'm not completely sure to understand how the setting you are discussing, but if more generically the question is whether the cost function is enough to assess whether the model is good at predicting or not, this question is complicated in the sense that it depends on what you mean by enough. It depends on the application. You may define multiple costs and evaluate your prediction performance according to different notions of costs. Okay. But generically, this is not what people do. I don't want to fake that I know, but let's say everything I've heard of and read about is always going the direction of selecting a cost that we think makes sense for some reasons, because, for example, in the quadratic loss, the probabilistic motivation behind that is that we assume Gaussian noise, Gaussian corruption of the data. In this case, you should minimize the quadratic loss, and I will explain why in detail at some point. But you may have another model of noise in mind, in which case it's better to consider another type of cost. But whatever you have in mind, that you at some point you should define a cost and stick to it, and use that as a metric of goodness. Yeah, I don't know if it answers your question, but the question of how to define the cost is not necessarily trivial. It's not simple. Okay, maybe if you define the cost in one way or another way, and you train the same model in the sense that you take the same hypothesis class and you train it using one cost or another one, it will not give the same results. and it's not clear which one you should take a priori, okay? And maybe to select which cost you should choose, maybe you can do cross-validation, which means you train your model according to the 2 different costs, and then you choose the one with the best prediction error on the test data. This is cross-validation. See you, Maria Aurora, Natalie Castillo. See you soon, Friday. So, is there any other question? Okay. All right. So anyway, I'm there Friday to answer more things. All right. So I strongly advise you to do 2 things, to maybe spend like 20 minutes to run the code and gain some intuition, and maybe spend an hour or whatever amount of time you want on reading the bias variance trade-off, because next time I will be more formal. I will do actual computations. So it will be more mathematics, and maybe it helps a bit if you read in advance, at least to understand the setting. All right.
I wanted to ask, is there any way how we can access the recording? At some point?
Yeah. At the moment, they're on my computer, but they will be online at some point. Okay.
Okay. Thank you.
All right. Okay. See you, everyone. See you on Friday. Good evening.
Thank you.
Bye. Thank you.
Thank you. Bye.